All right. Well, good morning, everyone. Welcome. If you're looking for the great expectations, obviously that's not this presentation. I am Morley. I'm a threat hunter with Countercept, and I'm going to be talking today about KillSuit, which is part of the Equation Group's exploitation framework from Danderspritz. My colleague Lacey, who did co-research with me, can be here today, so I'll be doing this solo. So, first of all, let's quickly go over what we're going to be covering today. We're going to break down into what KillSuit is, how it works and how it behaves and the actions that it can do. And then we're going to get to the crux of the research, which is what happens when it's installed, how it persists on a host, and equally how you can detect and remediate these infections. So obviously this breaks down to the first question is, what is KillSuit? So KillSuit is a post-exploitation capability modular mechanism. It was developed by the Equation Group as far back as 2013. It was then leaked by the shadow brokers in 2017 in the Lost in Translation leak. The Equation Group are, although it's not confirmed, they're strongly suggested to be associated with the NSA. This makes this a state actor level exploitation mechanism, which is obviously makes it exceedingly sophisticated. If the association between the Equation Group and the NSA actually does pan out, that's equally interesting because at the time, back in 2013, the NSA had an agreement, the PRISM program, which was an agreement between the NSA and several companies within the computing industry for access to things like encrypted emails and communications. But parallel to this, they developed this exploitation framework to have unauthorized access to Windows systems and also other such frameworks. KillSuit is included, as far as we know, within the Danderspritz and United Rate framework. The Danderspritz framework we know because that was inside the leak. The United Rates framework includes it as the instruction manual that has direct references to KillSuit installations. So that's just a basic overview about what KillSuit is. But more interesting is what KillSuit does. So KillSuit is a post-exploitation capability mechanism. So it's a bit of a mouthful, but what that exactly means is quite important. So we drew a diagram to try and illustrate what exactly that means. So where the pedal cheap agent is the malware that is deployed by the fuzzy bunch, can be used by fuzzy bunch to exploit, and the Danderspritz framework communicates with the pedal cheap agent on an infected host to then install KillSuit. So KillSuit is installed after the fact. KillSuit allows for lots of different malicious capabilities, and equally it allows for additional modules to be stored underneath instances. So KillSuit breaks down into instance types and module types. And some KillSuit instance types have particular malicious capabilities, whereas module capabilities tend to be capacitive in their nature for each of those instance types. One of the instance types actually allows for a pedal cheap agent to persist through reboots using their advanced bootloader SolarTime or SOTI, which we'll cover in a lot more detail later. So each instance and module, as I said, has a different capability. This is a list of some of the instance and module names that we know of. As you can see in the top left, there's a pedal cheap instance type, which is specifically for persistence of the pedal cheap agent. And these all have very unique functionalities. But as I said, there's instances and modules, and knowing how they fit together is quite important. So instance types, like Knave is Magic Bean, so is Sobernave, and Wraithrath, all have different malicious capabilities, which I'll go over in a moment. And each instance type can have multiple modules installed underneath them. These modules tend to facilitate additional functionalities for those instance types. One of the things that's actually worth noting is that KillSuit has the capability for operators to inject their own customized modules, which aren't necessarily already within the framework as we found it. We couldn't find a way to actually how these modules are created, but it's definitely something worth looking into. as obviously that widens it open to so many other malicious, nasty methods. Although we run through some of the code names, as I said, we're going to quickly run through some of the capabilities. It wasn't the focus of research, so I'm just going to do a basic review of some of the ones that we know about. So, as we said about Magic Bean. Magic Bean is a Wi-Fi man in the middle instance type. Basically, it allows the infected host to act as a man-in-the-middle operator. The instance type installs drivers necessary and injection tools to allow for the operation to take place. And basically, it does this capability. So an infected host suddenly can redirect traffic, it can inject things, it can capture them as it sees fit, which is quite cool. Next one is Dark Skyline. Dark Skyline is not an instance type, it's a module. So this can actually be installed under any instance type that KillSuit has. And this basically allows for complete network packet capture. The interesting thing about this is that the packet capture capabilities of this can actually be quite tailored. So you can do it for specific web services or anything like that. Once the operator has decided that they want to get their stuff back, it actually formats the captured packet into a PCAP file before transferring it back to the operator through KillSuit's encrypted traffics. Everything to do with KillSuit is encrypted. So everything inside the operation is encrypted, everything inside the instance type is encrypted, and all the communications are encrypted using instance type specific keys. So each instance will have its own different encryption for each installation. Next one is Sober Knave. I actually really like this one, although it's a bit rare to use. So if you have an air-gapped machine and you're somehow able to infect it, you can actually, this enables the Wi-Fi, if there's a Wi-Fi card installed that's just disabled, it re-enables it to allow for exfiltration using their encrypted channels back to the operator. So effectively bypassing, if there's only Ethernet, you can then have another traffic for exfiltration. The last one I'm quickly going to go over is Flu Avenue. Now, Flu Avenue is really cool. Flu Avenue and Dorman Gauze are the two custom TCP IP stacks that the Equation group built for KillSuit. And basically, they avoided detection by not touching the WinSock API. They completely wrote their own stack. So this, on a lot of occasions, avoids things like netstat analysis or any logging that would be to do with that API. In practice, it also tended to circumvent a lot of packet capture tools. During operation, we did have a couple of Wireshark instances on there, but the traffic seemed to be very isolated for the amount of traffic that we knew was going through. So how it actually got around using that was really cool. It also has the capacity to do DNS redirects and things like that, so it allows you to basically pivot and create your own sub-network through infected hosts, which was really cool. So, as I said, we've just very quickly gone over a few of these capabilities. The capabilities were actually, so the main research for the capabilities was actually done by a guy called Francisco Donoso. So if anyone really wants to look more into this, do look at his work because his stuff is really good on this. There's a lot of that list of the instance types that we have. Most of them we still don't know what they do. So if anyone's interested, do look at that. So now we're going to move on to the crux of our research, which is what happens when KillSuit's installed. So our research was to find indicators of compromise for KillSuit on a host, based on active installation, legacy installation, and their persistence mechanism. So what exactly happens when they burrow into a system? So to do this, we use these criteria. The attacker machine was based on Windows 10 with the lost in translation leak basically deployed and enabled. Each victim host was Windows 7 Pro, which was freshly installed each time. We used dynamic analysis, API, Regshot, the standards. Static analysis, we used Radar 2 for both the binaries for the framework itself and for the memory dumps of stuff that they injected into, so we could see what was going on. We also actively adapted scripts inside the framework to obviously get a specific output for different variables to see exactly what was going on. We're going to focus on KillSuit, so we're not exactly going to focus on how you compromise hosts using things like Fuzzy Bunch, because that's been investigated to death. We're going to quickly go over how we did compromise. So we've built this little table. So the attacker will use one of Fuzzy Bunch's exploitations, Eternal Blue, that everyone knows, Eternal Romance, so on and so forth, to get a foothold on the victim. It will then use double pulsar to inject a DLL pebble cheat payload into an active process. Standardly, this is LSAS. However, the operator can decide which process they want to inject into. We use calculator because it was much easier to filter through on that one. Once it's got running, it then calls back, or it can be listening. We got it to be active after about 93 seconds, which allows the DNS operator to connect to the pedal chip instance on the host, and that then gives an active agent, which gives bidirectional C2 connection and command and control. So now we know how we got it all set up. What is the weird stuff that happens when KillSuit is installed by pedal chip on a victim? So one of the first things that we noticed so we tried to focus on things that happened repeatedly in each installation, so we could find consistent indicators of compromise. The first thing we saw is that it kept checking the system setup in progress registry key. Now this is used for the OS running state between setup and regular running states. This happened at the beginning and the end of every installation for KillSuit. Now this check isn't exactly super abnormal. I mean, it is a bit, but it's not out there. But what we did do is we tried to configure the value to two of its defaults, so 0 or 1, and it made no difference what the value was, which was quite interesting. So we then started speculating on, was it looking for a customized value, a value that wasn't meant to be there? We tried loads of different variables inside there, but we couldn't actually get it to behave any differently. So we began to speculate that instead there must be another component of the framework that once it's installed must inject something in there that if the value is then corresponded to, it acts differently. But we tried every tool that we could find and we couldn't get it to misbehave. So although it was consistent, it's not the greatest indicator of compromise on that one. So instead we looked at for something a little more odd than just the OS running type. And we came across what I like to call the James Bond function, so system function 007, which is an advanced API call to the kernel, and it's used for NTML hash generation using MD4. Now this was obviously found in calculator, so there's no reason calculator should be doing this. So that stood out anomalous for that particular process, but as I said, because you typically ingest into things like LSAS, that, depending on the process, can be a typical operation. So if an operator's clever, obviously they won't put it into calculator. So this, although anomalous in some aspects, isn't consistently anomalous. But what was interesting is that when it called this, the hash that was generated was then stored in a registry value. Now, the registry value was OEM management, or OEM MGMG, with these two 32-character randomized directories. When we looked into that, we saw that this, on each installation, would inject into a different registry location. There's a tool within the framework called Double Feature. Now, Double Feature is used by the framework in order to basically build up a summary of what has already been done to that victim. And you can find down here that the KS module store root matched up to the registry that was injected into. Now, keen eyes might notice that the OEM management and drive management are actually different. That's because there's quite a few of them. This is just some of the ones that we observed during our research and our examination of the tool. But what you might notice is that it seems to be broken up into 2 bits. So you've got the capital letter in the top left, so you've got driv, and then you've got cache. And you'll see that they're repeated. And we found that these would then constantly be repeated in different configurations depending on how many times we installed it. And so we thought, we're onto something here. We then had the hypothesis that this is 2 separate lists being concatenated together in a randomized function in order to make it as difficult as possible to plan it. So we started on that premise. And we had it confirmed when we found the concatenation operation of 2 different string values in order to make this directory. So once we had this and we had it confirmed that this is 2 separate bits being spliced together, we knew if we can find these lists, we can find every combination that KillSuit used to install this modular encrypted database into systems, and obviously that would make it easy for legacy detection. So we started focusing on finding these lists, and we broke it down in 3 areas. We break it down into whether the the directory was communicated from the attacker, from the operator, to the agent, whether the directory was decided when the payload was first configured and built before being transferred over, or whether the payload itself would decide where to put it dependent on variables to do with that individual system. So the list would be stored in the payload, and then use variables it would then decide from those lists. We quickly eliminated the idea that it was hard-coded into the pedal cheap agent because reuse of the payload didn't generate the same results. So we knew it wasn't hard-coded into the payload. So we then moved on to whether it was decided from the attacker. And to do this, we had to break down how exactly the DNSPITS framework communicated with the pedal cheap agent when it was doing KillSuit operations. And this breaks down into this sort of flow. So the DNSPITS UI would then translate the user input through various internal libraries before handing it off to the core binary, which would then communicate with the pedal cheap agent, which in turn would then act with the KillSuit instance and the associated database. So we began looking at how the user input interacted with libraries. So the DEMI library, or the Decibel Minute library, we concluded very quickly was specific for KillSuit interaction. Every single functionality for KillSuit goes through this library. And we found that this particular one, so HelloConnect is used for dynamically load and unload different modules within a KillSuit instance. So once we'd isolated this, we started breaking down how this worked. So it seems to basically configure a message structure, which is then sent to the MCL tasking RPC perform call. So we followed that functionality, and that brought us to a separate library, the DSC library. Now, the DSC library performs this action, but it does so by importing a private library from elsewhere, the _DSC library. Now, this is important because all interactions with the pedal cheap agent seem to go through this private library. And we could find no reference to it in any of the library files that we could find. Now, this created a problem because if we wanted to understand how this works and how it communicated and ideally where these lists were stored, we thought we had to get access to this private library. So we actually started looking into the core binary by analyzing it statically to find any references to see if we could understand how this was done. Analysis of the binary showed that there were references to several functions within the private library. But we found that it was actually a external CPython module library that was injected at runtime. So doing it statically, all the associated address were empty. Although we could find references and error capturing for the functions, the actual commands themselves were not stored in the binary as it was. So we then moved on to dynamic analysis of the binary, but that in itself had a number of other issues. So the guys that built this, the Equation Group, had obviously put into mind about people doing this, and there were a lot of countermeasures for analysis. One of the most basic was that it actually detected hooks for debuggers and would instantly terminate if it saw one. So that instantly was a red flag of they've done this to avoid analysis. We were actually able to disguise the debugger and still get it to work, but even then, all of the addresses where data was loaded for this library were loaded and unloaded as soon as they were required. And the index table for different functionalities had multiple references to the same function, but a lot of them were dummies, and it seemed to move about, which seemed very, very difficult. And because of that, we were actually unable to find this private library within the runtime, the debugging of the runtime binary, which was disappointing, to say the least. But we concluded that if we couldn't clarify if it was there, we could at least try and clarify that it wasn't decided at the payload level. So then we could focus our research even further. So to that, we then moved on to analyzing the pedal cheat payload as it was run, and then when it tried to do KillSuit operations on a victim. But this had a number of other problems. So looking at the stack of when the pedal cheat agent was injected into, we found that the values and the functionality of the agent were, instead of being injected into the process as we would expect, it was actually injected into the kernel. and we couldn't exactly figure out how they'd done it. So it was injected in a way that we couldn't actually retrieve the values that we were looking for. So although we knew the pedal chip agent was injected into a specific process, we were unable to actually extract the data we were looking for. So because of this, we actually got to a last resort where we reverted back to trying to use their own code against them. So inside the framework, there was a pedal cheap analysis tool, or PC prep, that you could use to display internal values of the payload. And although this provided a lot of information about how a payload was meant to behave and what it was communicating to, so if you could find one, you could obviously find out a lot of information about how it was designed to behave, it didn't include the values we were looking for, anything to do with tables or values or anything to do with the registry directory that we were looking for. So again, we had to conclude that this has eluded us in this point as well. We weren't exactly happy at this point because these two lists, we knew they were in here, but we were unable to find them, and we'd exhausted our level of capability for reversing these tools, basically due to the level of sophistication they put into to prevent us from looking at them. If anyone has any expertise in obviously looking at this or is interested, please talk to me after, because I'd love to get like other people working on this, because that list is, that I can't find it, it's really annoying me. But although we couldn't find it here, we didn't give up. So, you know, you learn how to fail and you carry on anyway. So we went back to the installation and we began analyzing in minute detail all of the different operations that happen. And we started to cross-reference all the different installations to see if there was anything that promoted a pattern. And eventually we came across this, which is a cryptographic provider type. Which was referenced at each fresh KillSuit installation for a fresh pedal cheap agent, but only on the first installation. Now, the reason this stood out to us is because it occurred each time. So we investigated type 023 and the provider type. The first thing to note is, what is a cryptographic provider type? So a cryptographic provider type is basically a description on how an encryption algorithm is to be used and what values they're to do in order to get the output that they require. So Microsoft includes a number of them by default for RSA, AES, and so on and so forth, so that it's uniform across all of their machines. And it has types 1, 3, 5, 12, 13, 18, and 24. It does not have a default value provider type of 23. So this provider type is actually an abnormality from the default values that Microsoft provides. This was further proven by looking at the provider type table that Microsoft provides, although their documentation isn't always full. From all the instances that we saw, nothing seemed to deviate from this from any system that we looked at. There's also no reference to a type 023 provider type anywhere that we could find. Historically speaking, there have been instances of type 023 being in systems, but this has typically been because of so a bit of history. Back when Windows NT4 was out, it was commissioned to be used by UK government, but GCHQ mandated that it had to have a customized cryptographic system in place. So they actually built a customized version of Windows NT4 with a customized provider type inside that would then be used for their communications. So you could speculate from that this tool might be trying to detect whether this is a custom build of Windows to try and find specific targets, but that is just speculation. So from this, we did find that type 023 was a consistent installation point across all instances, and from that, we had some success. So we had a mixture of a semi-conclusive list of registry directories that we got through our experimentation. Although we didn't have the lists themselves, we found that the registries that we were seeing started to repeat each other. And obviously, if you then splice them and see that each section of them was being repeated in different configurations, you can therefore get every combination of permutation from the list that we have to generate quite an extensive list of the places where it could be stored. Although, unfortunately, we can't say for sure that it was conclusive. We also found that the type 023, because it was uniform, allowed for a active installation detection by basically examining registry queries. So from those 2 points, we had both a legacy installation and an active installation detection point to focus on, which was quite cool. But although this is the active installation, what about persistence? So I talked earlier about SOTI. So It persists using the SolarTime bootkit, which was built by the Equation Group. Now, this is an extremely advanced bootkit for the time. It works by basically injecting into the bootloader of the system, and it allows for all KillSuit instances to be rebooted per each boot. And as I said earlier, KillSuit instance can be configured in order to reboot the pedal tube instance, allowing command control of an infected host. This is the only one that we know to work up to supported Windows systems, so it works up to Windows 7 on legacy boot. It doesn't work past Windows 7, but obviously Windows 7 is still supported and widely used, so this is something of interest. But first of all, how does Windows 7 boot? So to understand how SOTI affects a machine, you need to understand how a system boots itself up. So a system works by obviously powering on, initiates the BIOS, which communicates with the hardware and does hardware checks. This in turn loads the master boot record, which then loads the active partitions, which in turn knows where the operating system files are, and then loads the bootloader for that operating system. SolarTime focuses on this area. So the transition between the master boot record and the active partitions handing off to the bootloader. And in this section, the system looks something like this. So the master boot record will load the volume boot record into its own memory location, basically to overwrite itself in live memory. That in turn will then start the initial program loader, which loads the file system and the boot manager location, and then hands off the control to the boot manager, which then loads the operating system. So let's get down to what SolarTime does. How does SOTI work? So it's first worth noting that SolarTime has been encountered before under the name of Greyfish by our friends over at Kaspersky Labs. And they basically did an overview about how it acts within the system and the sequence of events that happens, but they didn't give a lot of technical detail about what changes were made in the system in order to allow this to happen, or how to remediate or detect it. So that's where our research came into it. The setup that we used for our research was Windows 7 SP1 using a IDA Pro GDB debugger. Infection was the same as the previous one, so using Fuzzy Bunch with Vendana Spritz. And the persistence was KillSuit persistence, pedal sheet persistence using KillSuit in order to analyze SOTI in greater detail. So let's get right into the crux of it. So what does SOTI do to be bad? So this is so the first thing it does is actually it prevents boot error logging by changing this value inside the MBR. So instead of using a hold command, which would then cause a system error and then cause error reporting, it instead makes this jump command back to its own location. So it will just loop indefinitely, preventing it from error reporting. So if SolarTime ever fails to boot, or for whatever reason, there are some checks it does later that could cause it to crash, it will never tell the operator about why it's happened and will never give any information, which is quite an elusive method. We thought that was pretty cool. The next thing is that the initial program loader location is typically 77A, but SolarTime actually changes this. The reason it does this is that 77A, instead of having the initial program loader, it injects a number of SolarTime specific datasets, and it does this for operations that I'm going to cover later, which is really funky. But because it injects it at this location, it has to move where it then loads the IPL. So within the IPL, it will do these flag checks, which are again not normal. So rather than just loading the index root before handing off to the boot manager, instead it will do an ECX register check to see if it's set, and if so, it will load a customized index root, which will contain the malicious boot manager location. Now, although this checks whether it's set, when SolarTime was installed, we didn't find any instance or method to unset inside the configuration, so we're not sure why it checks this registry flag. All we know is that it does. And this can be seen more clearly here. So it injects this check. And if the check is unsuccessful, it still loads the original uncustomized index root. So it has the capacity to load normally without SolarTime, even though it's injected SolarTime, which is a bit odd. So although these changes are odd, where exactly does it hand off to malicious code? So this can be seen in the IPL, where at the bottom here, it actually injects a jump to its malicious code at 93AE. This is basically its attempt to change the control flow and allow it to start doing its nasty work. Once it jumps to this location, what exactly does SolarTime do? So first of all, it does a BIOS interrupt 15. This basically gives it information on how the system is configured, what type of memory it has, what memory length it has, over 1 megabyte, and other system information. If the memory type is what it requires, it then enables access to memory over 1 megabyte by activating the A20 bus line. And once it's enabled this extra memory, it loads the MFT table records in order to find a object ID file within the MFT records. Within this object file, it then sets the index root of that file for for the location of the hidden boot pack. Now, the index root of an object ID file is not called index root, it's actually called $O. Now, IPL programs don't typically look for this, so how does SolarTime know what it's looking for? So earlier, I mentioned that SolarTime had to change where it jumped to for the IPL. That's because in the same location, it actually injects the definition for the index root of an object ID file so it knows what to search for. But it also injects decryption keys and methodologies and methods for its payload that will be used later on. So it has to move the IPL reference for these 2 bits of key data. So using that defined $0, it's now able to extract the index root of the object ID file in order to search for its malicious bootloader that's hidden inside one of the references. But how does SolarTime know what value is written into and where the malicious actor is? Well, to do that, we have to look at how a index entry is actually created. So an index entry is formed up of these individual parts, but you might find that between align 8 and VCN, there's no defined length, and that's where SolarTime injects the it's the offset from the starting cluster of the MFT. So it basically installs the offset from the beginning of the MFT file to where the malicious file is stored within the file system itself. Now, so it can search through for any value in there and find the value it's looking for, any value that's injected into that point, and extract it and then look for the file. This we found corresponded to a true type font file, which is where it actually stores its malicious kernel, which is the malicious kernel driver, which is then used for the bootloader. Using the check.soti script within the framework itself, once you've compromised a host, you can run this script to see what SolarTime files have been injected. So in this instance, we found that davidbi.ttf was injected. But following that script, we actually found a list of all of the TTF files that can be used in order to store this malicious kernel driver, which is pretty cool. So once the boot pack is loaded into memory, so once it's found this malicious kernel driver, what does it do with it? Well, it loads the malicious kernel driver into memory, and then using the functionality that was stored in the IPL location, it then decrypts the packet using the key that was stored at the location. The key that's injected into the original IPL location is generated using CRC2 hash, which is basically a hash of the malware, which is just done 1,000 times. And it then uses that hash generated by that to decrypt it. It then calculates the hash of the internal malware against the hash that's been stored in the decrypted malware to see if they correspond for an integrity check. If the integrity check passes, it then hands off controllers to the boot pack. And after that, all of the KillSuit instances will be loaded, pedal chip instance can reinitialize, and so on and so forth. So that's how SolarTime functions. But the crux of the matter is, how do we detect and remediate if KillSuit is on a system? So we've gone over how we can see if it's installed, what it does when it's installed, what SolarTime does once it gets onto a host, how it persists, but how do we detect and remediate these points? So for installation, it breaks down into the type 023 cryptographic provider type, which is done at each first installation by a PPCC agent. The system function 007 kernel call, which although can be anomalous depending on the process, is not conclusive as depending on what the operator has injected into. Presence of any of the permutations of the registry directories that we talked about earlier. The list, we have a full list that obviously you guys can access, that I can give references to. And there's also this blank box. So at the end of when we were coming to the conclusion, we rescanned through the framework itself and we came across a driver list. Now the driver list couldn't say the number of drivers that were related directly to KillSuit. They're KillSuit loader drivers. Now the loader drivers are used when instances are first initialized. Although we found this driver list, we couldn't find any instance of these drivers being loaded during our research. However, we speculated that they were installed and then uninstalled as fast as they were physically possible, or they were used at SolarTime, with SolarTime in order to create the persistence. But we were actually unable to find any reference of them. So although this is a point of interest, it's not a conclusive method for detection. But it is something that you could easily plug into a detection system in order to just regulate if any of these, there are a large list of drivers and if any of them are present. So this gives a method for legacy installation and operational installation. So although we know we can now detect whether it is being installed or has been installed, how do you get rid of KillSuit if it is on the host? So KillSuit operates in this fashion. So the boot pack, the PPCC instance, and the running instances all communicate with the encrypted database within the registry. So if you remove the registry, all of those functions cease to activate. So the SolarTime has no KillSuit data in order to boot. The running instances don't have their module stores, so they don't know how to act. And the PPCC agent has no index reference for the registry in order to know whether KillSuit modules are installed. So it can't communicate or perform any actions. So removing the database is the most effective way of neutering KillSuit. The location of the database, as I've gone over several times, is obviously within one of those registry locations, but there are others that we may have not seen. But if KillSuit is installed but SolarTime isn't, rebooting the system will do it because it's all running in active memory. It doesn't drop the disk unless you install SolarTime. So how do you know if SolarTime is installed? So earlier on, we quickly grazed over some of the changes it makes. And one of the things that it does is it changes this section to use two not operations before a jump to the IPL control. So we focused on searching for those two NOP commands where they shouldn't be. To do this, we actually adapted PyMBR, which is an open source script for analyzing MBR files, and instead injected this get BBR file with a SOTI detection for bytes 267 and 268 for the NOP operations, and essentially saying if these two values are found in this location where they're not meant to be, SolarTime is installed. Which on all instances of testing we found to be accurate. So every time we installed SolarTime, running this script identified it correctly. So this was a conclusive method for detecting it, which was super awesome. But although we know we can now see if SolarTime is installed using this method by analyzing the VBR records, how do you stop or remove SolarTime? Now that's more tricky because SolarTime installs itself at multiple levels, including the firmware. So the firmware level shows that they had access to production sort of level access in order to change the firmware code. Equally, SolarTime is heavily encrypted. As we said, it uses this injected a decryption system in order to actually access the malware. So it bypasses a lot of AV systems that will look into this sort of data. And basically, in order to prevent SolarTime from functioning, you need to sign manufacturers need to sign their MBRs, their BBRs, all of their sort of firmware in order to prevent alterations. Now, as we said earlier, this works on Windows 7 up to legacy boot. However, UEFI and Windows 8 forward using secure boot prevents this. Because the checks are put in place, SolarTime can no longer function because the checks detect it and obviously prevent it from making alterations in the first place, or preventing the malware from functioning. So yeah, bit quick. Any questions? Okay, yeah.
Do all of the modules use that database, or is it just SolarTime and
the Registry Encryption database? Yeah, so all the KillSuit instances created their own instance within the Registry database. So that OEM management reference, all those different configurations, each instance would have its own injection into the registry. And under that, each module, the 32-bit randomized character after that, would be each module that was installed under that. So some instances have, by default, I think 3 modules installed, whereas some of them only have 2. So depending on the instance type, you can see which modules are installed. And equally, if you then install a custom module underneath that instance, or say Dark Skyline, for example, for packet capture, that will then be injected under that registry location as well. But it's all encrypted.
Have you considered creating a custom module that just blows out that database so you can see it bright red?
We did look into making custom modules, but we couldn't actually figure out how the hell they built them. So we found references to, obviously, because of how it works, we found the scripts that obviously references the data, but we couldn't find when the modules themselves were actually stored. So we couldn't figure out how they were coded or anything like that. They used to use a custom scripting language, which was specific for the DynScripts framework. So we suspect that because these original modules were built back then, they may use the same scripting language. But we were unsure at the time. But that was a thing we did look into. Anyone else? All right, cool. Thanks for listening.